Welcome to the Mesh Energy Cooling with Heat Pumps Masterclass. The aim of this masterclass is to go through some of the basics of reverse cycle cooling with heat pumps. All of Mesh Energy's webinars can be found through MESHWORK, the details of which are on the screen now. Today we'll cover the following: an introduction to Mesh Energy, the energy hierarchy, some of the basics of ground source and air source heat pumps, some terms and definitions, the energy hierarchy in more detail, what a heat pump is, and how it cools. We'll then move on to some of the more technological parts, determining the cooling load, the benefits and disbenefits of using a heat pump to cool, passive cooling using a ground source heat pump, active cooling with heat pumps, cooling using the underfloor heating system, cooling using fan coil units, heat recovery and reuse, and finally combining cooling with solar PV. We'll then take a little look at some of the financial aspects, including the effect of cooling on domestic RHI payments and the investment case for installing cooling with heat pumps. Finally, we'll look through some next steps, some of the key points of the presentation, how you can work with Mesh Energy, and finally there's a space for questions. So who are Mesh Energy? Mesh Energy are an independent energy consultancy based in Farnham in Surrey. We're your partner in building a low carbon future. We're independent energy consultants, and our aim is to guide and simplify the energy landscape for you. We offer holistic and impartial advice, and we don't believe in a one-size-fits-all type situation. Let's look at some of the basics. We'll start with some terms and definitions, as these are important to understand some of the later parts of this presentation. Sensible heat gain is the energy added to a space by conduction, convection, or radiation. Latent heat gain is energy added to the space when a moisture is added to the space by means of a vapor. This could be through people or from things like plants. The space cooling load is the rate at which energy must be removed from a space in order to maintain a constant air temperature. Effectively, the space cooling load is the addition of the sensible heat gain plus the latent heat gain. The dew point temperature is the temperature at which air reaches saturation. That means that it reaches 100% relative humidity, and condensation will begin to form at a given humidity and pressure. The relative humidity describes how far the air is from saturation. 100% relative humidity would mean that it's at saturation point. Cooling the air will increase the relative humidity because the ability of air to transport moisture is reduced as the temperature is reduced. And finally, the energy efficiency ratio is similar to the COP of a heat pump. It's the amount of thermal energy that can be removed from a cool space for a given unit of electrical energy. A high EER is good and a low EER is bad. Let's look at the energy hierarchy. This is the basis of all of Mesh Energy's work. We start by looking at the building location, orientation and form and trying to optimize these in order to reduce both heating and cooling loads. We then look at the fabric element design. That means the design of each part of the building, be that walls, windows, roofs, etc., in order to reduce both the heating and cooling loads of the building. We also look at air tightness and ventilation. Increasing air tightness has the benefit of reducing both heating and cooling loads. However, air tightness must be balanced with good ventilation to ensure the comfort and health of the occupants of the building. This is where things like MVHR come into play. Finally, we'll start applying renewable technologies to offset any remaining loads on the building. And finally, we look at things like appliances and lights. Appliances are key to understanding cooling, as the heat generated by appliances will provide part of the cooling load. And finally, we look at the use of the building. Changing user behavior is very difficult, and hence it is at the bottom of the energy hierarchy. However, there are things that users can do in order to reduce their energy consumption. In conclusion, follow the energy hierarchy, eliminate cooling requirements through good design, and make economically viable and visually acceptable fabric improvements before specifying renewable technology. So this is the basics of how a heat pump works. You'll see on the screen a diagram showing a basic refrigeration cycle. Heat goes into the evaporator. The refrigeration cycle effectively amplifies this heat to turn it from low-grade heat to high-grade heat. The heat is then exported from the condenser of the refrigeration cycle. The refrigerant gas then turns back into liquid through the expansion valve, where it's cooled and goes back to the evaporator, where it can gather heat again for the next time around the cycle. As you'll see, the refrigerant never leaves the circuit. It's always part of this refrigeration cycle. So low-grade heat is harvested from a heat source. It passes into the evaporator. This raises the refrigerant temperature slightly and turns it from liquid into gas. A compressor then compresses and raises the pressure of this gas, which increases its temperature. The heat that is in this gas is then transferred through the condenser, and the condenser also turns the gas refrigerant back into liquid. It's then passed through an expansion valve, which reduces the temperature and pressure back to where it can enter the evaporator. So, in a heating cycle, you put the inside of the building on the condenser side, and you put the heat source on the external side. So the heat pumps extract low-grade heat from the heat source, whether that's an air collector or a ground collector. They convert it into high-grade heat, and that high-grade heat is used to provide space heating, domestic hot water, and occasionally swimming pool heating. During the cooling season, the refrigeration cycle is reversed. This means that the outside is now where you're ejecting heat that you don't want, and the inside is being cooled. Now, that is done by means of a four-way valve within the refrigeration cycle. Heat is removed from the building and simply rejected into the environment. Although we'll see later how some of this heat may be reused. This is an air source heat pump. You'll see it has two major components: an external box, which is where the air passes over the evaporator and collects heat, and then some sort of internal unit. Depending upon the type of air source heat pump, the lines connecting the external unit and the internal unit may be refrigeration lines or maybe water lines. Air source heat pumps take energy from the air. They're powered by electricity, and they provide warm water for heating, chilled water for cooling. They provide heat for domestic hot water, and they can also provide heat for swimming pool heating. Typically, when in heating mode, they'll give an efficiency of between 250 and 400%, or a COP of between 2.5 and 4. This means that for every unit of electricity you put in, you can expect to receive between 2.5 and 4 units of heat. The outdoor fan unit is used to collect this energy. A ground source heat pump works in much the same way, it just uses a different heat source. Again, it's powered by electricity and provides similar levels of heating and cooling. However, it also has the option of free cooling, where heat is transferred into the cool ground loops during the summer, and this helps to recharge the ground loops for the following winter, when you'll be extracting heat to use for space heating and hot water. Typically, ground source heat pumps are slightly more efficient than air source heat pumps in heating mode, giving a COP of between 3 and 5, or an equivalent efficiency of between 300 and 500%. Pipes are buried in the ground to collect or eject heat. So the first thing when we're creating a new heat pump cooling system is to understand what the cooling load of the building is. This will vary from day to day, but largely depends on the following. Heat conduction through external elements such as walls, roofs, doors, and windows. Solar radiation, which comes in through transparent surfaces such as windows. Heat conduction through internal elements. This is particularly important where you have areas of the building which are cooled and areas that aren't, such as in the example shown on the right. And internal gains from occupants and equipment. This could be simply the heat given off by people in a room. Typically, a room which has a high number of occupants may see a significant cooling load simply from the heat given off by those people. The final type of gain is ventilation gain, which is simply the warmer air outside the building being brought into the building and adding to the heat of the building. So why would you cool with a heat pump? Well, firstly, it increases the occupant comfort. Most people find a room temperature of between 21 and 25 degrees quite comfortable. So typically we'll try and keep room temperatures within that kind of range. There's less additional plant when compared to specifying a dedicated air conditioning system. You're not duplicating external fan units, for example. When using ground source heat pumps, the waste heat from the cooling side may be used to recharge the boreholes, and this can reduce the number of boreholes required and hence the capital cost of drilling them. You may be able to use the recovered waste heat for other uses, such as domestic hot water heating or swimming pool heating. However, there are downsides to cooling with a heat pump. It adds to the complexity of the installation when compared to a simple heating-only installation. There will be a requirement for fan coil units, as well as underfloor heating, to deliver the best comfort. There's always a risk of sweating and condensation from chilled water pipes, as can be seen in this diagram on the right-hand side of the screen. Will there be sufficient power from the heat pump to provide all the cooling necessary? Often we find that cooling loads are significantly higher than the space heating loads for a building, and usually heat pumps are specified with the peak heating demand in mind. Therefore, it may be that additional cooling power is required to supplement that provided by the heat pump. There will be an additional level of control complexity due to the additional burdens being placed upon the system, and we'll look at those in more detail later on. And finally, there is a loss of green credentials from the project because cooling is not considered an essential service and should be designed out wherever possible. So green buildings generally are not equipped with cooling equipment. So let's start with the most basic type of cooling, which is passive cooling from a ground source heat pump. In passive cooling, the heat exchangers of the heat pump are bypassed in order that the natural coolness of the ground can be used as a source of cooling. I'll draw onto this diagram the basic system. So cool water, or brine solution as it's often known, is brought into the heat pump. Through this pump, it bypasses the normal refrigeration heat exchanger and goes to a secondary heat exchanger called the free cooling heat exchanger. It then passes through this heat exchanger and back out of the system through this 3-port valve and back out into the ground. On the other side, water from the heating and cooling circuit is brought into the heat pump. Here it's diverted through the free cooling heat exchanger and back out into the cooling circuit. The compressor, which is part of the refrigeration cycle, does not run, and therefore there is much lower energy consumption because the compressor is the main user of electricity. So in summary, passive cooling relies on the natural cooling effect of passing warm brine through the ground collector. Here, heat is lost to the ground and can be stored ready for the following winter. During passive cooling, the refrigeration circuit is turned off. The system uses the naturally low temperature of the ground during the summer months to provide cooling. Because the system is very cheap to run, because the compressor is not used, the system is often referred to as free cooling or natural cooling rather than passive cooling. It should be noted that the cooling effect of passive cooling is relatively low compared to that of active cooling, which we'll look at shortly. Active cooling is by far the most common method of cooling with a heat pump and can be used with both air source and ground source heat pumps. It effectively reverses the refrigeration cycle so that the component that would usually be the evaporator becomes the condenser, and the component that would usually be the condenser becomes the evaporator. Heat is rejected to the air in an air source heat pump or the ground in a ground source heat pump. When heat is rejected through a ground source heat pump into the boreholes, it recharges the ground, and this may be used to help offset some of the capital cost of installation, as the boreholes then don't have to be quite as large. It should be noted when cooling with any kind of heat pump that the lower the temperature difference between the source and the fluid you're trying to use, the better the energy efficiency ratio or the coefficient of performance of the system. And this can be seen in this graph. Generally speaking, many systems are specified with cooling water temperatures of between 7 and 10 degrees. And this gives a worse EER than if you specify higher cooling temperatures, such as 1215 or 1821. However, the downside of this is that the cooling capacity of the system would be reduced. Chilled water pipes must be insulated to prevent condensation or sweating, as it's otherwise known. The chilled water can then be fed to fan coil units, chilled beams, or underfloor heating to provide the cooling in the room. Generally speaking, fan coil units are the most efficient method of cooling. Let's look at cooling with underfloor heating. This is the simplest integration of cooling in a heating optimized system. However, it has drawbacks. You'll almost certainly already have some sort of underfloor heating system in a new property with a heat pump, so it makes sense to try and use it for cooling, doesn't it? Well, unfortunately, there are lots of reasons why it's not such a great idea. The first problem is that if you're cooling the floor, you're also reducing the dew point at the boundary layer between the floor and the air around it. And this means that there's a very tight limit on how much you can cool the floor without forming puddles. Secondly, warm air rises, and if you're chilling the floor, surely what happens is you get stratification within the room, and the warm air will collect at the top of the room and you'll get cool air at the bottom of the room. And this isn't great for occupant comfort. And thirdly, because of the limitations of the floor temperature and the risk of sweating of the floor, you can typically only cool the room by a few degrees Celsius when using underfloor heating as the transfer. However, it can be paired with free cooling to give a very low cost comfort cooling, and this is often used by developers as a nice sales tool, and it can provide a small amount of additional occupant comfort. However, if we want really good quality cooling in our house or in any building, probably the best method is to use fan cool units. Fan cool units are served by a chilled water circuit. This means the water is below ambient temperature and will form condensation. However, this condensation can easily be managed, and the cooling performance is very closely matched to that of air conditioning. Fan cool units can be either mounted on the wall or the ceiling, and can be used for both active and passive cooling. Each fan cool unit must have its own condensate drain, and this means that there must be some sort of connection to drain away that condensate. Where fan coil units are also used for heating is they can be used also for heating. However, it's usual to pair fan coil units with underfloor heating to give the greatest occupant comfort, and that's because people tend to like low air movement when they're in a heated room. Let's look at some other innovative systems that can be used to recover and reuse heat that's been rejected from the cooling. In this system, which is typical of an ecoforest heat pump, you can see that they have an additional heat exchanger labelled Hdr. The Hdr heat exchanger allows for simultaneous heating and cooling, where the heating is used to provide heating for domestic hot water or a swimming pool, while the cooling can be used for both. The cooling side can be used for both heating during the winter and cooling during the summer. This is a highly efficient system because it allows reuse of waste heat. During the winter, when the system is in heating mode, as is shown in this diagram, the typical hot water temperature maintained will be around 45 degrees Celsius. And this is good from an efficiency point of view and is typical of most heat pumps. However, during the summer, when cooling is in operation, that heating water temperature for domestic hot water can be raised as high as 70 degrees. And the waste heat can be directed both to domestic hot water or to a swimming pool. Finally, let's look at some controls. This is a typical controller made by a company called Tightness. It allows both heating and cooling management and will control the speed of fan coil units. Controls are required when specifying heating and cooling from a heat pump. First of all, you'll need some sort of thermostatic control to control when there is a demand for heating and when there is a demand for cooling. Secondly, when you're cooling with underfloor heating, you'll need some sort of humidity control to prevent sweating of the floor. When cooling or heating with a fan coil unit, you'll also need some sort of fan speed control. When using underfloor heating, especially with wooden floors, you'll need some sort of overheating protection for those wood floors to prevent them going above a predefined temperature, which will be set by the flooring manufacturer. Often this temperature is around 27 degrees. And finally, you'll probably want some sort of time scheduling and maybe some sort of remote control through a phone app or similar. This will allow you to operate the system in the most efficient manner. Let's look at the combination of cooling and solar PV. Now, often when we talk about PV and heat pumps, we realize that actually they don't complement each other very well in many circumstances. That's because the peak heating demands and the peak output from PV systems are unlikely to be well matched, because obviously heating demands tend to be highest in the winter when the output from solar PV systems is lowest. However, cooling is different because the peak demands of the cooling system and the peak output from PV are quite well aligned. So cooling can work really well with PV because both systems tend to be near their maximum working point at the same time. Cooling loads may be significant when compared to other electrical loads, especially during the summer, so it's important to take account of this when sizing the PV. You should also consider using control strategies to maximize the use of PV for cooling. This may mean having a simple time clock so that at times when the PV output is likely to be highest, the cooling is enabled, and at other times the cooling is disabled. However, you could use more advanced strategies where you actually monitor the amount of output from the PV system in real time and use that data to help control the cooling demands. And here is a typical final design. We can see on the right-hand side of this photo the heating side of a typical system with a parallel buffer and a hot water cylinder. And on the left-hand side of the photo, you can see the cooling side with a cooling buffer, the cooling expansion vessel, and all the cooling circuits going off to the various parts of the building. Obviously, this is expanded for clarity, but it gives a nice idea of the kind of pipework that might be involved. And this is how it looks in diagrammatic state. Let's have a look at some of the effects on domestic RHI and other government subsidies. So domestic RHI doesn't directly allow for cooling. However, it doesn't prevent you from using a system that allows both heating and cooling. Cooling loads themselves are not eligible for RHI. However, where there's heating loads, these are eligible and would be assessed in the same way as a heating-only system. Because most systems in domestic RHI use deemed use for heat loads, this means that most systems will not require any kind of additional heat metering. However, in more complex systems, it may be that you'll need to use heat metering, and this might be more complex when cooling is taken into the equation because you need to be able to differentiate between the electricity used for heating and the electricity used for cooling. Let's look at the investment case. Cooling can rarely be seen as an investment in its own right, except for the fact that it obviously increases occupant comfort. However, there's no payback on cooling because you're not offsetting this cost against anything that would otherwise be there. So we'd always advise reducing the running costs by following the energy hierarchy, and that means reducing the cooling loads at design stage. Then consider whether passive cooling could be used instead of active cooling, as this is an order of magnitude cheaper to run than active cooling. Then offset some of this cooling cost by using the waste heat for other purposes, such as domestic hot water or swimming pool heating. And finally, offset the electrical cost further by installing solar PV. And finally, when using chilled water, try and think about the set temperature of this chilled water, as the higher the set temperature, the better the EER of the finished system. So I'm going to go through 8 takeaway steps. First of all, carry out a CIBSE TM52 or TM59 analysis to determine whether the building is likely to overheat and will require cooling. Secondly, improve the building fabric, and repeat these TM52 or TM59 calculations to reduce the cooling loads to an absolute minimum before adding any technology. Thirdly, calculate any residual cooling loads using a thermal model. You'll have needed to prepare a thermal model to carry out step 1, so this shouldn't be an additional cost. Step 4. If you're using a ground source heat pump, consider whether passive cooling alone may be sufficient to meet the cooling demands. 5. Consider the method of heat transfer. Are you going to use fan coil units or some other method? In most cases, fan coil units will be the most appropriate choice. 6. Consider how the system will be controlled. What additional controls will be required over and above a standard heating system? 7. Can waste heat be used elsewhere, either for domestic hot water heating or for a swimming pool? And finally, step 8 is, can we combine our cooling system with some other technology, such as PV, to reduce the running costs? So, how do we get Mesh Energy involved in all these design decisions? Well, Mesh can get involved from stage 1, right at the beginning of a project, by producing a feasibility study, energy and SAP calculations, or even just drafting some simple space layouts. Then, as we get through more into detailed design, we can do a full design and specification, a mechanical and electrical package up to tender stage, and provide installer recommendations. We can then review tenders that come back to check they're compliant with the specification and provide installation oversight. And finally, post-occupancy stage, we can provide post-occupancy evaluation, including energy monitoring and air quality monitoring. The upcoming webinars in the next couple of weeks are the Mesh Energy Renewables Refurb, how to get an existing building ready for renewables, and a guest talk from Dr. Stephen Finnegan, where he talks about embodied carbon. If you've got any question, please post them in the comments below and we'll do our best to answer them. Thank you for your time.